Hey, and welcome. Today, we're jumping right into the world of kinematics, which is the science that lets us describe and, even predict the movement of pretty much everything around us.
So, how in the world can we predict where a moving object is going to be at any given moment? I mean, it seems unbelievably complex, right? But the physics behind it all is a field called kinematics. And that's exactly what we're going to break down right now. Kinematics is a huge branch of classical physics, and it is laser focused on just one thing: describing how objects move. It doesn't get into the weeds of why they move, the forces involved. That's a whole other story. It just gives us the language to talk about the motion itself. Honestly, the best way to think about it is like you're learning a new language. To really understand the story of an object's journey, we've got to get a handle on the basic vocabulary first. Once we know the words, we can start telling the whole story.
So, what are these essential words in the language of motion? Well, it all boils down to just a few core concepts, and these are the absolute building blocks for everything that comes next.
First up is displacement. Now, this is not just the distance an object travels. No, it's how far it's moved from its starting point in a specific direction. So let's say you walk 5 meters east, and then you turn around and walk 5 meters west. You've walked a total of 10 meters, sure, but your displacement is 0. You're right back where you started. Next, we have velocity. People mix this up with speed all the time, but just like displacement, velocity has a direction. Saying a car is going 60 miles per hour, well, that's its speed. Saying it's going 60 miles per hour north, now that's its velocity. See the difference? And finally, acceleration. This is any change in velocity, and it is not just about speeding up. If you slow down, that's acceleration. If you take a turn, even if your speed stays exactly the same, your direction is changing, which means your velocity is changing. And yep, you guessed it, that's acceleration too. So these concepts give us 5 key variables that physicists use for any motion with constant acceleration. We use the symbols s, u, v, a, and t. And these 5 variables, they are the absolute foundation for every single calculation we're about to dive into. Okay, now that we've got our vocabulary down, we can finally open up the physicist toolkit for motion, the kinematic equations. These are the powerful formulas that connect all 5 of our variables and let us make some seriously cool predictions. You know, the secret to cracking pretty much any motion problem, as long as the acceleration is constant, isn't some wild, complicated theory. Nope, it all comes down to 4 elegant and incredibly powerful equations that just tie everything together perfectly. And here they are. This is the whole shebang, the 4 core equations of kinematics. It's kind of incredible when you think that this simple toolkit is all you need to solve a huge range of problems, from a falling apple to a launching rocket. But hey, here is a massive pro tip, especially if you're studying for exams. On the official Cambridge data sheet, you're only given 2 of these 4 equations. So to really truly master this topic and be ready for anything, you absolutely need to know all 4 by heart. Seeing these equations is one thing, but watching them in action, that's where it all really clicks. So let's put our new toolkit to the test, shall we? Let's solve a real-world problem. This is where the rubber meets the road. We're taking the abstract tools we just learned, and we're going to apply them to a concrete problem. This is exactly how physicists bridge that gap between theory and reality. So here's our challenge. It's a classic physics problem. A stone falls from a cliff. It hits the ground 3 seconds later. The question is simple. How high is that cliff? To tackle this, we can use a simple, super reliable 3-step method. First, you just list everything you know and what you're trying to find. Second, you pick the right tool for the job, the right equation. And third, you just plug in the numbers and solve. Easy as that. All right, let's do step 1 and list our variables. The displacement, s, which is the cliff's height, that's our big question mark. The problem says the stone falls, which is code for its initial velocity, u, being 0. We don't know the final velocity, v, and we don't need it, so we'll just ignore it. The acceleration a is from gravity, so that's a constant 9.81, and the time t is given right there in the problem, 3 seconds. Okay, now for step 2, choosing our equation. We just look at our list of variables. We need to find s, and we know u, a, and t. So we just scan our toolkit for the one equation that links those 4 variables. And there it is, the perfect fit. S equals ut plus 1/2 at squared. And for the final step, we solve it. We plug our values for initial velocity, acceleration, and time into that equation, do the math, And there's our answer. The height of the cliff is 44.1 meters. It's just a fantastic illustration of how these powerful equations can turn a real physical question into a pretty straightforward calculation. You know, solving an exam problem is great, but the real power of kinematics is in its real-world applications. This isn't just about passing a class. It's about understanding the world. I just love this quote because it captures the scale of it perfectly. Wherever there's movement, from planets orbiting a star to cells moving in your own body, kinematics is there, running the show. The examples truly are infinite. I mean, just think about it. A self-driving car is constantly using kinematic equations to predict where other cars are going. An athlete launching a javelin, a NASA engineer charting a course to another planet, even a video game designer trying to make a character jump realistically. They all rely on the fundamental principles we just covered. And that brings us to one last thought. We started this whole thing with a simple falling stone, but these exact same rules govern the cosmos. It really makes you wonder, if we can so perfectly predict the motion of something small, what are the real limits to predicting the motion of our entire universe? Something to think about. Thanks so much for watching.